So as an ex-runner, you get that little bit of energy for the last lap, don't you? You look as if you've got some energy left. So here goes. So first of all, I'd like to thank the organisers for asking me to give this talk. Quite often you give talks and you know what you're going to give. This talk made me think, and it hurt. Because they challenged me to think about model coupling. I was really delighted to be asked to think about model coupling because I think it's something that really needs addressing. But I was really concerned about thinking about model coupling because it's really hard. But it's an important problem that's well worth addressing. Let me just say, these two talks I've just heard were fantastic. Excellent talks, both of you. And it sets the scene for what I'm going to say. And in fact, there's an awful lot of overlap and consistency across the set. But as Paula said, I'm coming at it from a different angle, a different perspective. I am a computer scientist. I usually get a better reaction than that when I say it. Come on. Thank you. Thank you. So this is me. I include this bit in the right to impress the farming community, and I said over lunch, I'm impressed DEFRA, if they're in the audience, and I was sitting opposite a DEFRA person who was duly impressed. So I work the land, I'm a smallholder. But the bit in the left is the bit that matters. Now there's some mathematicians in the audience, so you may be able to spot a regime shift as you go down this list, a change point. And the change point occurs after the first bullet point up there. So historically, I was a classic computer scientist. I am a distinguished professor of distributed systems. Does that not sound impressive? And then suddenly my world changed. I get drawn into your world. Everything from then on down is cross-disciplinary. I started meeting you guys and I loved you. I had to work with you. I was drawn in. So everything I do now is using my skills as what can I bring as a computer scientist to help solve problems of the natural world. And it's a really privileged position to be in. So I'm approaching this as a computer scientist thinking, what tools can we bring to help environmental scientists solve big problems, global challenges of our day? That's what I do now. But the past, distributed systems, surely this helps in model coupling. So as soon as I was given the challenge to think through this, I went back in history. Now, just to explain the structure of my talk, what were people doing at the weekend? I can tell you where I was. So I'm going to structure my talk around 3 headliners. And thank goodness Emily Evis did not invite Leonard Skinner, or it just would not have worked. The first one's a little bit contrived. A perfect storm of complexity, Stormzy. A little bit contrived. The other 2 work better, I can assure you. Did anybody watch Stormzy? Just one? Come on. I didn't watch them either. So, complexity, that's what computer scientists are good at. If I'm teaching a distributed systems course, this is one of my first slides. It's easy, isn't it? You have the complexity of the underlying brackets distributed infrastructure, lots of computers all connected up with each other, really complex. And then you just introduce some middleware. And you give people a high-level programming abstraction and they use that. All the complexity is hidden. Job done. Yeah, we can go home now. We can go to the pub. But it's not like this. There's been a massive amount of research into that little box called middleware. And there's a whole community that's convinced they've got it right. There's middleware platforms out there that give you platform independence, language independence, abstraction, can mask out problems of consistency in the underlying distributed system. All sounds really impressive. The sobering thing is that it's all wrong. It just does not work. Now I step into my new world, your world, and say, right, middleware for model coupling. Is this any use? No. So I could actually have a subtitle here, The Arrogance of the Single Discipline. Because if I step back into my old world, computer scientists are convinced they've cracked this problem. I step into the new world, it doesn't work. So why does it not work? Well, it doesn't work because of the sheer complexity we're actually having to deal with now. There's actually two parts to this. One is the increasing complexity of distributed systems. I'm not going to talk much about this, but I'm happy to discuss it later over a beer. Very important. Distributed systems are really complex these days. You've got cloud computing processing the data, connected to lots of sensors and Internet of Things of the natural environment, connected to mobile phones, really sophisticated distributed infrastructure. Middleware doesn't work in these complex, what I call systems of systems. The complexity is run away from us. We don't know how to program these things. That's one story. But then you move into the environmental sciences world and you think, well, we're going to couple two models together. How hard can that be? How hard can it be? But then you get to the killers. That one works better. Did anybody watch the killers? Oh, slightly better. I thought they were fantastic. What kind of audience is this? I'm a bit worried there might be a whole bunch of Cure fans in the audience. So this is where there's a lot of overlap with Ian's talk, I'm very pleased to say. These are the killers. Middleware has an obsession with interoperability, getting A to talk to B. That's the easy bit. But let's now look at the hard bit. In your world, you've got two models, or actually multiple models you want to couple. What do you need to achieve? Well, let's go around this jigsaw. First of all, Ian already mentioned what I would call semantics. He was talking about data dictionaries. You need to know what the outputs of one side are and the inputs of the other. And you need to have that well documented. You need ontologies to understand exactly what they are, or you cannot even begin to reason about interoperability. And once you know what they are, you might have to scratch your head, because how do you transfer them? There may be a transfer function in there from the outputs of one model to the inputs of another model. That might be really complicated. There might be as much sophistication in the transfer function as there is in some of the endpoints, in some cases, and it's not thought about. Scaling, we've heard a lot about scaling, particularly this morning. There may be sophisticated downscaling going on. So as well as transferring between different types, you might need to downscale what you have to the fact match the scale of the other model. Does middleware help you with that? Absolutely not. Something's going wrong here. Maybe there'll be good news later. Maybe with the cure. And then, of course, uncertainty. There's been plenty of said about uncertainty. Here, surely you want to reason end-to-end in a model chain about uncertainty. Now that must mean some model of underpinning uncertainty, so you can look at the propagation of uncertainty and reason about it in this model chain. What does middleware give you for that? Zilch. And then in the middle, I've put something that's an acronym from computer science, quality of service. It represents the management of the network and the distributed system. In the modern world, if you have some data streaming from a field, let's use this as an example, you have some soil moisture data and you're monitoring it in a field. You don't necessarily want to propagate all that data from all the fields in the UK back to the cloud. You might want to push some analysis into an edge device. Excuse me for some of my terminology. You might want to do that in an edge device. You might want a model that sits there and then communicates to the cloud when there's something happens, when there's sufficient levels of soil moisture content that there's a risk of a water quality incident. That's when you want to communicate. So you might have a sophisticated infrastructure that's between the two endpoints that manages the network and the distributed system in the way it does a job for you. Does middleware do that? No. I'm going to pull your leg a little bit here, if you excuse me. It's always interesting how in integrated modeling diagrams you see big boxes and little arrows. Sorry, sorry Mark, you had quite thick arrows, so I was relatively pleased at that. When I look at that, I think it should be big boxes and big arrows, big thick arrows. Because what I'm arguing for here is that the connection can be as important as the model and can be as sophisticated. And that's not to mention issues around the heterogeneity of the models at the endpoints, whether they're statistical models or process models or what they are. And it doesn't talk about feedback loops. So it's getting complicated. So, on to The Cure. Who watched The Cure? 2! Well, beat Stormzy. I didn't. They're vaguely irritating backdrop to me growing up, so I went to see Christine and the Queens instead, which was fantastic. Now, I'm going to step through 3 steps of the solution. How long have I got?
Some minutes.
Oh, 2 minutes a step. How do we overcome this level of complexity? Now, the first step was actually, I looked back in my historical notes. In 1996 in Cambridge, there was a project called ANSA, Hills Road in Cambridge. Most of you are looking at me thinking I wasn't even born then. What are you talking about? This is historic. The curious thing is it's been forgotten about, because what this project came up with in an associated standard, RMODP, what they came up with was an architecture of distributed systems which involved endpoints and bindings. So if you were building a distributed system, you would build your endpoints, which would what we call services or microservices these days, and then bindings. And bindings could be arbitrarily complex. So the wonders of that project is that they recognise the importance of coupling, and that coupling can have as sophisticated a software architecture as what you have at the end. That was a fantastic project. Look at modern day middleware, and that's gone. It's been forgotten about. You know, if you're looking at service-oriented architecture or cloud architectures, the emphasis is all in the complexity of the end, and then there's a thin wire between them. And it's wrong. It's the wrong model. These networks can become really sophisticated, and unless we've got an abstraction that represents that, we're stuffed. Step 2. Wouldn't it be great if we had such a coupling framework where you could compose a coupling engine that does the job you need so that you can couple them together? And these various Lego bricks here involve things like downscaling algorithms, transfer functions, things that manage the network and the flow of the network so the data is delivered as and when you need it. In my ideal world, you would have a nice high-level description that allows you to describe the kind of coupler you need, and it would be generated. That's not beyond contemporary computer science. It's very doable. Would that be good? Oh, that didn't go down well. One nod. Oh, another thumbs up. This can be done with the right will and the right collaborations. We can have a coupling architecture that steps you on from basically mailing files around and then somebody getting the file and looking at the numbers and thinks, what is this? And then the final step, and this is where also injecting an advert, final step is virtual labs. I believe that such a binding framework or coupling framework should be a core component of what we in Lancaster and also in Seeds with Paula are focusing on, which is virtual labs. Labs for doing science that are collaborative environments with building blocks to really make it much easier for you guys to run models in the cloud, to couple models, to carry out visualizations of the end results. So this is, in a nutshell, what we're trying to achieve in a project we have. Data science of the natural environment, maybe unfortunately known as Disney. No competition there. We're trying to build experimental virtual labs for different challenges, one of which is landscape decision making, which Paula is leading on. The other ones are ice sheet melt and air quality. So looking at big scientific questions and trying to understand how do you construct a virtual lab that supports that collaborative science. And as a subtext for that, how do we support the coupling of models within this environment? And that's ongoing work, but I think is very relevant work for the debate we've heard over the last few days. So I think I'm about done. Thank you for listening and being a great audience. You did manage that last lap very well.